Good. So yeah, Cauchy sequences, construction of reals. You can find this in the notes. Tomorrow we're gonna have a temporary office hour. 1 to 2. Because of the homework, because of homework 1. Simply join weekly classes. So we will construct the reals using what is called the Cauchy completion. The strategy is simple. We will define the reals as the limits of rational numbers. So for that, we need a general concept called the Cauchy sequence. This will come up later as well when we talk about general metric spaces. A sequence is called Cauchy. If for every epsilon positive, there exists n epsilon, so that for all m and n bigger than n epsilon, you have am minus an is less than epsilon. Okay. So it says that you can find an epsilon, after which you can there's a disk. So that they're all within this disk. So, okay. Well, I don't like this. Anyhow, okay. So an example. For okay, any questions? Okay. For an, just the harmonic sequence. Fix epsilon positive and set fix epsilon positive. Then choose n epsilon over 2 to be the upper floor function, ceiling function of epsilon over 2 plus 1. Okay, then take m and n bigger than epsilon over 2. Use triangle. So 1 over m plus 1 over n. By monotonicity, these are both less than n epsilon over 2. And then you use your definition for n. So you get, 2 times epsilon over 2, which is just epsilon. Okay, so 1 over n is a Cauchy sequence. A more general example, so more generally, any convergent sequence i.e. an goes to L is Cauchy. Okay. All right. First, I want to go through let's go through some properties for them. So this is one of them. Where are some other properties? Good. So every Cauchy sequence is bounded. We'll prove that. And let's also do the subsequential. So a Cauchy sequence that has a convergent subsequence. A and k going to L implies is also convergent. an goes to same limit. And one property we will use. Yeah, I will do the, so sum of Cauchy sequences is Cauchy, that's clear. That's not very hard to prove. So I will leave it to you. But I want to prove that suppose Cauchy an is bounded below then meaning an is bounded below by epsilon naught for all n. Then the reciprocal is also Cauchy. Is converse true that all, let me see. Yeah, the so question is the converse true that all Cauchy sequences are convergent? So we will do this today. It is true for the real numbers. Yeah, so it is true for the real numbers, but there are other spaces where this is not true. So yeah, let me write it here. The converse is only true in what is called the complete spaces, which we will talk about it later. It's only true in complete metric spaces, like the reals, like e.g. Real numbers. So let's prove some of these things. Let's prove the bounded. That's very easy. Okay, so what do I want to do? Right. So for epsilon equal to 1, there exists an epsilon positive such that am minus an is less than 1 for all m comma n bigger than n epsilon. Okay. Right, so that tells you that, namely, right, it tells you that an epsilon minus epsilon, an epsilon plus epsilon, that you have upper and lower bound M1 and M2. For all n bigger than n epsilon. And then the question is, what about n less than n epsilon? Right, but these are finitely many numbers. So let S1 to be the min of A1, AN epsilon, AN epsilon, and M1, and let S2 be the max, A1, AN epsilon, M2. Then I think it's clear that what you get is for all n, you get S1 is a lower bound of AN, and S2 is the upper bound for all n starting from 1. Okay. What is AN epsilon? Right, so there exists some n epsilon. This is from Cauchiness, Cauchy property. So we don't know exactly what n epsilon is. In the example above, n epsilon, for AN being 1 over n, n epsilon was 1 over epsilon over 2 plus 1. So it changes. So it's not concrete, but it's given by the Cauchy property. So that's property 1. What was 2? Oh, the subsequential. Good. All right. So want to show that A and K going to L implies AN, the mother sequence, also goes to L. Okay. Why do we any epsilon? So why do we choose epsilon 1? Any epsilon will have been fine. Yeah, any yeah. All right. So fix epsilon positive. Good. Now by Cauchy, there exists n epsilon over 2, so that AM minus AN is less than epsilon over 2 for all NM bigger than n epsilon over 2. By A and K going to L, there exists n tilde epsilon over 2 bigger than n epsilon over 2, such that an k minus L is less than epsilon over 2 for all nk bigger than n tilde epsilon over 2. Yeah, so we put these two together. We have an for all n bigger than the max. No, I don't have to take max. Bigger than n epsilon over 2 tilde. We use triangle. Where we take nk. I should be more concrete. Let me take this to be n tilde epsilon over 2. This is the subsequence. From Cauchy, we get epsilon over 2 for the first guy. This is Cauchy. And we get another epsilon over 2 from the limit, the subsequential limit. All right, so together we just get epsilon, and that's it. So let the max be epsilon plus 1. See? So the question is, what should the max be? No, so I mean, we don't need. We're not asking for sharp inequality here. So you might have S2 to equal one of them. So if we wanted sharp, we could add +1 and then -1. So yeah, you could do that. So you can have -1, +1. So if you want sharp, bounds. Write S1 tilde equal to S1 plus 1, no, -1. And S2 tilde to be S2 plus 1. Is that okay, King Yang? Yeah, okay. All right, let's see. Yeah, let me go into constructing the reals, and if we have time, we'll come back to prove other properties. And I'll also type the proofs for some of these properties in the notes. Okay, so now let's construct the reals. So suppose you have two, suppose you have, so I mean, we have, how do you say it? We have two approximations. To square root 2, namely one from below and one from the top. And the question is, if you have uniqueness. So definition. Two sequences are called two sequences are called equivalent if for every epsilon positive, you can find n epsilon such that an minus bn is less than epsilon for all n bigger than n epsilon. Okay, so let's do an example. So so 1.1, 101, 1001, and so on is one sequence. And then the second one, 09, 099, 0999, um, 999, and so on, are equivalent. So why is that? First, we write them in decimal. So any questions? Yeah, the question is every real number, does it have infinite, does it have such sequences to represent it? And the answer is yes, because of what we will do now. You can have infinite nines or, you know, many zeros. But for irrationals, you have unique. Okay, so how do we do this? So in decimal, we have an is the sequence 1 plus 1 over 10 to the n, because this is 1, comma, 0, 0, 0, and then 1. And bn is 1 minus that. So first we show Cauchy. First Cauchy. So fix epsilon positive. Then I think it's clear. Pick n large enough. Large enough. So that 1 over 10 to the n is less than epsilon over 2. You can solve this if you like using log. Yeah. So you pick this to the n. Then an minus am is equal to 1 over 10 to the n minus 1 over 10 to the m. By triangle, this is less than this. And by monotonicity, you get 1 over 2, 10 to the n, which is less than 2 times epsilon over 2, which is epsilon. Okay. So that's why it's Cauchy. And then equivalence. An minus bn is equal to 1 plus 10 to the n minus 1 minus 10 to the n, which is just 2 10 to the n. So for the same n, we get epsilon. So they are indeed equivalent. So let's finally define the real numbers. A real number is defined to be the limit an for an Cauchy sequence. So of rational numbers an. Okay. Further, we say that two real numbers R1 equal to the limit of an and R2 equal to the limit of bn are called equal when are equal R1 equal to R2 if an and bn are equivalent Cauchy sequences. So returning to the example, an equal to 1 plus 10 to the n, and bn equal 1 minus 10 to the n, both converge to 1. Both converge to so limit of an, call it R1, is equal to 1, which is equal to R2, the limit of Bn. So R1 is equal to R2, and they both equal to 1 because they are equivalent sequences. That means you are free to write 0,99999 is equal to 1,000. Any questions? Do we have to prove that the sequences are Cauchy before equivalent? Yes, you have to prove Cauchy first. I will try to think of an example. Yeah. Why do we need to prove Cauchy in the example? Exactly what Levon asked. So we need equivalence requires a Cauchy. Real numbers are defined as the Cauchy limit. So, Nick, is that okay? Because the real numbers are defined as the Cauchy limit. But because the sequence is convergent, you get Cauchiness immediately. No, I meant to include it. So let me go back and I meant to write it. Yes. Yeah, so I meant to write it. Yes, thank you. 2 Cauchy sequences. Nick, is that okay? Okay. All right. Okay, so I mean, we're almost done. Let's see what properties we have. So proposition 5.8, the reals have the familiar algebraic properties. Have algebraic. Okay, let's see. So you can add them. So if you know R, if R1 and R2 are real, then R1 plus R2 are also real. You can also multiply them. And you can take reciprocal. So I will do the positive case, but the negative is the same. All right, so let's do the first one. So by definition, R1 is equal to some limit of AN, and R2 is equal to some limit BN, where AN and BN are Cauchy. Then we have that AN plus BN is also Cauchy. You can prove this. Right, is also Cauchy, which implies that the limit of AN plus BN exists. It's some real number, R. And then, right, so you have R minus R1 plus R2. But this is just the limit. The first guy is the limit of AN plus BN. Second guy is AN, BN. And then you use linearity of the limit. So is that okay? Yeah, let's do multiplication. So again, we have limits R1, AN, R2, BN. And then we'll show now, want to show that AN BN times BN is also Cauchy. All right. Good. So let's see, we have AM BM minus AN BN. You add and subtract. So AM minus AN BM minus BN. Okay. Then use that Cauchy sequences are bounded. So first use triangle. Okay, so far. Use that Cauchy sequences are bounded to get a bound for B and a bound for A. Okay. Now by Cauchy, choose. So yeah, fix epsilon And then by Cauchy, choose n to be the max of n1 and n2. So that so this is for an, and this is for bn, so that you have am minus an is less than epsilon over 2 times mb, and bm minus bn is less than epsilon over 2 times ma. Okay. So coming back, let me on the screen. So coming back, we have mb times epsilon over 2 mb plus ma epsilon 2 times ma. And so you're left with epsilon over 2, which is just epsilon. Well, I have a minute, so let me do the final one. Actually, no, I'll let me finish with the completeness. So we'll finish with completeness. Definition. A subset of S in R is called complete if every Cauchy sequence inside S converges. Right, so let's put the punchline. The reals are complete. So let's prove this. So given a sequence, so start with arbitrary Cauchy sequence an in R. As we showed today, an is bounded by bounded for some m. We can apply a Bolzano-Weierstrass. To get a subsequential limit. Is that okay so far? does it need to converge in S? So, yeah, it converges in S. I will. That's right. It has to converge inside S. Let me add it quickly. It converges to a point L in S. And then from what we proved today, as proved above, the mother sequence also converges. Due to Cauchy, the mother sequence converges to the same point. All right. Okay, so that's it for today. You have a tutorial at 12 for some of you, and I'll stick around for the rest of you to ask questions. And also tomorrow we have office hour at 1 to 2, in case you have questions for the homework and other stuff. So I'll stick around to ask your questions. The rest who have tutorial, please go to your tutorial. It's Patrice. So I'll stick around. Good. So Levon says, where did you get MB and MA? Where did you get MB and MA? So right, we proved that Cauchy Cauchy sequences are bounded. Levon? MB is not concrete. Is that okay? Or okay, yeah. Good. Is A S plus B a valid way to represent? Yes, it is a valid way. Yeah, Bing Yao, that, yeah. Yeah, sure, go ahead, Levon. In this course, we define this as rationals. Where cannot, no, it can. So remember, we had this, right, Levon asks, is 1.4124 exactly? Yeah, Bing Yao answered it. So this is a rational representation. But in general, when you have terminating decimal, we proved it. We proved in the notes that it would be rational. Levon? Levon? Yeah, is that okay? Levon, is that okay? Or you have a question? Shirley says, is MA and MB upper bounded? No. So let me write it here. BM is less than MB for all M, and AM AN is less than MA for all N bigger than 1. Shirley? Okay, correct. Yeah, exactly. Yes. Okay, for homework 1, question 1, are we allowed to start the proof ending in all zeros, or do we have to be more general? And yeah, so as we proved today, these are the same real number, whether you have all nines or all zeros. And so you're free to use either one, because from what we proved today. So Raghuram, is that okay? Raghuram? Okay. So in the problem set, isn't it enough to prove that there is an R between? Yeah, I don't know exactly what the homework. No, in the homework, I think they wanted you to have terminating decimal. They don't want you having repeating decimal. So that a rational number could also have repeating. And we don't want that. We want terminating. Levon, is that okay? Okay. For proving, okay, wait. So where are we? Shirley says, for proving max min, is it sufficient to show that the inf soup is within the set? Yes. So that's all you have to do. You have to prove that they're in the set. Is that okay, Shirley? Shirley? Is that okay? All right. What's next? I'm still here. Oh, yeah, let me respond again, Bisman. But by the way, Bisman, if you have problems connecting, please email me, because I don't know if students have issues. So let me know. Can you email me, Bisman? I want to know if you have serious problems disconnecting. So the answer is you can use either representation, because from what we proved today, they give you the same number. So is that okay, Bisman? Bisman? Okay, good. Can we take that the sum of, no, you have to prove this. And the proof is very short. It's half a line. That rational plus irrational is actually irrational. Try to do it by contradiction. Is that okay, Ahmad? Yeah, it's very short. Yeah. So irrational numbers only have one. Yes, they only have one representation. Yeah, they only have one. One way to see this is by definition. Irrational number is one where the decimal expansion does not repeat. The only non-uniqueness comes from infinite nines and infinite zeros. This is the only source of non-uniqueness. Is that okay, Swapnil? Swapnil? Right. Anything else? No? All right. So tomorrow we have an office hour, 1 to 2. Click on the same link and we can further chat. All right. Thank you.